Okay, so next we talk about different assumptions involved in the turbulent fluxes. Okay, here we know that for the thermodynamic equation, we can also see the covariance terms here. And these terms, they represent the turbulent fluxes. For example, this one is the vertical heat flux. Okay, the vertical turbulent heat flux, this one. It's vertical meaning this W here, and then heat is represented by the potential temperature, the turbulent potential temperature. And we also have the vertical turbulent flux of zonal momentum. So this is, the meaning of this is that the W prime, the turbulent vertical motion, is transferring the horizontal turbulent motion to different levels. Okay, it's the same as this one. Okay, and the magnitudes of the average turbulent flux divergence. So by divergence, we are talking about differentiate the covariance term with x, y, z. Okay, that's called the divergence terms. And then this is the average, right? We are doing the divergence. We are performing the divergence on the average of these covariance terms. Okay, so this is saying that these terms can be as large as other terms in the momentum equation, so we shouldn't neglect them because if we are talking about the PBL. So outside the PBL, the fluxes terms are too weak to be considered, so that's why you don't see them in other courses. Okay, so the divergence of the covariance terms can have some effect on the mean variables. It can increase or decrease the variables, the mean variables in time. Okay, so we have a closure problem in here because if you have 3 unknowns and 3 equations, then you are able to close the set of equations. But here we have a lot of unknowns. We have, first of all, we have 1, 2, 3, 4, 5. We have 5 equations here, and we have more than 5 unknowns. First of all, we have 5 unknown mean variables, which are these ones. And then we also have a lot of unknown turbulent fluxes in the first 4 equations. Okay, so to solve this set of equations, we need closure assumptions. We need to make assumptions to these terms so that we can reduce the amount of unknown variables in the equations. Okay, the first assumption is that we are always away from the regions with horizontal inhomogeneities, which means that we don't want horizontal variation in our domain or in the area that we're studying. Okay, we don't want to be next to the forest, and we don't want to be next to mountains or lakes or anything. No horizontal variation. So that's why we can cross out the horizontal variation terms. We only leave out the vertical change in here. Okay, we also cross out the advection terms by the horizontal wind. Okay. The second assumption is that in the PBL there will be very little or no subsidence. So the average vertical motion will be very, very small, so small that we assume that it's 0. Okay, so we know that with fair weather, the average of the vertical motion is very, very small. It's between 0 and 0.1 meter per second. And the vertical velocity fluctuations, which is the turbulent vertical motion, usually change over 0 to 5 meter per second. So this is even larger than the average value. And that's why we make the assumption that the vertical motions are very, very weak. Okay, and then we can cross out this term too, and then these. So the total change would just be the local change over time. Okay, so here we have a profile, the vertical profile of the potential temperature over height, and assume that we have heating at the surface and buoyancy produced. That's why we have an unstable profile in here, statically unstable environment. So theta is decreasing with height, unstable profile, and we assume that there are two particles moving up and down adiabatically. And by adiabatically, we should go in the vertical way, whether it's up or down, because we should keep the theta constant, right? When we are rising or sinking adiabatically. So theta stays the same. Okay, so this air particle is going up, for example, which means that W prime is larger than 0 because this is going up. And then when you are here, you are warmer than the environment, which is from this profile, which means that this is an upward heat flux because omega prime is positive and theta prime is also positive. You are warmer than this one, so the deviation would be positive. Okay, which means that you have an upward heat flux. Okay, and then the second particle, if you're here and then you are displaced downward, then this one will be negative because you are downward, right? And then this one would also be negative because you're colder than the environment. Okay, so hot air rising and cold air sinking both means that you have net upward heat flux. So when you are having eddies like this, you are doing a lot of turbulent mixing and creating a more homogeneous fluid. So this kind of motion is actually making your profile even more adiabatic, more vertical, more closer to the neutral profile. Okay, so we have the net transport of the turbulent quantities. So this is not 0. Even though there's no transport of mass, we know that the average of the the turbulent vertical momentum is 0, so there's no net transport of mass, but heat is transported up. Okay, which means that we have to also look at the covariance terms. Okay, so in this case, the turbulent eddies transport heat upward, so this is the covariance term is positive, and this tends to make the lapse rate more adiabatic. So this is the lapse rate of the environment. So this kind of upward heat transport is making this profile more vertical, closer to the neutral profile. Okay, so I have a question for you here. I also have the answers. So farmers use this kind of theory to protect their crops from freezing at night. How do they do that? They use motor-driven fans to generate turbulent eddies, and the eddies mix the warm air down and cold air up. Well, basically, they are driving some eddies, and then the eddies will bring the cold air up, and then the warmer air from above down, because the surface is cooling much faster because you have radiative cooling, and the farmers make use of this vertical turbulent transport to keep their crops warm. Okay, so next is the vertical turbulent transport. So now we have crossed all these three terms in here. All we have left is the total change of the potential temperature profile over time and the divergence of the vertical turbulent flux. Okay, this is becoming this one because we are crossing these three, and then all we have left is the change over time, the local change over time, this one. Okay, and then we have crossed out these three, and then all we have left is this one, so I'm putting this on this side. Which means that the divergence, or here the convergence of the heat flux will warm up or cool down that layer of atmosphere over time. That makes sense, right? You have heat flux changed over height. Okay, so here we have made some closure assumptions by assuming a certain profiles to the flux divergence terms. If we make some assumptions to this flux divergence term, we can solve the set of equation. Okay, here is showing you the observations from the real atmosphere. You can see that this is measurements by aircraft flying in the boundary layer. So you can see that the oscillation is quite vigorous. The heat flux, this is coming from the heat flux. Okay, if we do the average of it, it would be a very, very small number. Very small number. This is the average. But you can see that sometimes there are a lot of spikes in here, even very high spike in here. Okay, there is another way to do analysis. If you have data, you have the W prime, the turbulent vertical motion term, and then we have the turbulent potential temperature term, and then we can also do the histogram for the heat flux, and we know the preferred values for the heat flux in that area. Okay, what we should do is that we should also study the profile of the flux of the covariance terms. If we know the change of this over height, we know this term, right? And then we can know if it's cooling or warming. Okay, here we have the heat flux profile, and then we can calculate the change over height, and then we can know if it's cooling or warming in the atmosphere. And here, depending on the slope of your vertical transport of horizontal momentum, then we can calculate the change of the U-bar over time, and this one also. At nighttime, they're too weak, so there is nothing to discuss in here. Okay, so the first question will be making use of Taylor hypothesis to calculate the size of the eddies. And then the second one is that we are having measurements at different levels, one level and then second level and third level, 3 levels in here. And x-axis is time, so they are the time series of different measurements. Okay, so what you need to do is that you need to make use of the signs showing here. There are no values, right? The signs showing here to find out the situation for the heat flux. And then you will know if the heat flux is increasing or decreasing with height. And then you can find out if, because you know this, and then you can find out if the air is warming or cooling. Make use of the equation that we have just talked about. Okay, and here you need to fill in the blanks, larger or smaller in these 4 boxes, and then you know that if it's upward or downward heat flux, and you also know that if your air is warming or cooling, or you can't tell. Okay, so here is mathematically giving you the profile of the heat flux according to height, and you need to find out if the air is warming and does that depend on the height. Okay,